Hello everyone, and welcome to AISC's live webinar, Where Did That Force Come From? Combining Diaphragm and Brace Frame Forces. Today is October 23rd, 2014, and we are very pleased to have everyone joining us today. My name is Brent Liu. I am with AISC, and I will be moderating today's presentation. I want to introduce today's speaker, Raphael Sabelli. Raphael is the Principal and Director of Seismic Design at Walter P. Moore. Raphael earned a Special Achievement Award from AISC as well as the T.R. Higgins Lectureship Award. He is active in the development of seismic design standards for steel systems and is a member of the AISC Seismic Provisions Committee, the ASCE 7 Seismic Task Committee, and the NIST Building Seismic Safety Council's Provisions Update Committee. Raphael is also currently the chair of the AISC Seismic Design Manual Committee and was the project manager for the 5-volume SEOC Seismic Design Manual. Very pleased to have Raphael presenting today. Welcome, Raphael. I'll hand things over to you.
Thank you, Brent. So today's webinar is entitled, Where Did That Force Come From? Maybe that doesn't give you perfect picture of what we're talking about. This diagram is intended to focus us a little bit more. What we're after today is a design methodology that permits us to make sense of the different requirements that we find in ASCE 7 and in the seismic provisions that AISC publishes, and how they come together when diaphragms meet braced frames. So this is my method of reconciling the two sets of provisions. There's a bit of a gap between what the two tell you, and I think it takes a little bit of engineering judgment to bridge that gap. And so I will be honest up front that what we're talking about today is not code requirements, but simply my engineering judgment, which you're welcome to use or discard as you see fit. So we have, in the design of these connections, many different joints. And each of these joints needs to be designed, and we need to derive some design forces for those joints. We also have different lateral loads. We have lateral loads for which we design the braces and their connections. We have lateral loads for which we design the diaphragms and the collector connections. And somehow we need to reconcile them as we come together in the design of this large assembly of joints, this connection here. In order to keep things relatively simple and consistent, I'm just looking at vertical and horizontal forces. There could be moments as well. I'm showing as part of this connection, I'm showing a joint here between the beam and the larger connection assembly. That may or may not exist in your designs. If it doesn't exist, then that's not a connection you have to design. But the method does give us the axial forces in the beams as well. This joint could be a pin sort of joint, as I've drawn here, or a fixed joint. If it's a fixed joint, there are also moments to be designed for. Those are not included in this methodology, but it's pretty straightforward to carry those through the connection and doesn't really require any comment. All right, there are different types of forces that we'll deal with. We'll have the main lateral base shear forces, or lateral forces that correspond to the base shear. These could be wind or seismic. Then we have the diaphragm accelerations for seismic, and these are F sub P forces that are inconsistent with the design base shear. Now, we do have diaphragm forces in wind design, but those diaphragm forces would be consistent with the design base shear. So it only gets complicated in seismic, where we have a new force introduced. We also have, for our higher R systems, our special concentrically braced frames, eccentrically braced frames, buckling restrained braced frames, we have a requirement to design the connection based on the yielding of the so-called fuse member of that system. So that introduces a new set of forces which are inconsistent both with the applied forces that give us the base shear, the design base shear, and with the diaphragm forces F sub P, and so those have to be reconciled as well. For clarity in this seminar, I've done color coding. So red here will mean the base shear forces, yellow will mean these diaphragm forces F sub P, and this color blue will represent mechanism forces. Before we start into the method, I do want to clarify the nature of the analysis that we're performing here. If you look up analysis in many textbooks, or structural analysis in Wikipedia for that matter, you might find a couple of different definitions. The first definition of analysis really points at a precise application of physical laws to essentially predict forces and stresses within a structure. So if you do your analysis and apply the forces, you should be getting the right stresses in each of these joints. That's a pretty ambitious definition of analysis, especially when it comes to seismic design, or wind design for that matter, where the exact nature of the forces is not known in advance, and we do we simplify those forces quite a bit before we apply them. So I would say that the second definition of analysis is a little bit closer to what we're doing, and that is deriving appropriate design forces for members and connections, so that for the type of load, for the rough magnitude of load that we predict, we'll get adequate performance. So we're not too concerned about exactly predicting what's going on, but we do want to get appropriate design forces so that we have strength to resist the application of forces that we anticipate. Now, turning our attention to the connection assembly that I presented in that first slide, I'm going to ask, when we're applying these diaphragm forces, what are the forces in the braces? The building code, ASCE 7, the AISE 341 seismic provisions don't really tell you how to answer that question, and hence we have this seminar. And I'm just going to say at this point, we can't assume the forces in the braces are zero. That doesn't seem to be an appropriate prediction, and more importantly, it doesn't seem to be, it would not lead to an appropriate design. It would lead to a design that might fail if the loads are, if there are any forces in those braces, any significant forces in those braces. So if it's not zero, we have to come up with some answer that we can use in design. In this seminar, we're going to start with wind and seismic base shear forces. We'll look at R=3 systems in the lower seismic design categories B and C. The only difference between B and C is that in C we apply the omega sub O factor at the collectors and their connections. Then we'll do a numerical example and try to solidify what we've done in the first half of the webinar. Then we'll turn our attention to the higher R systems. We'll do the ordinary concentrically braced frame, which is just slightly different from the R=3 braced frame. And then we'll spend quite a bit of time on the more ductile systems, the special concentrically braced frame, eccentrically braced frame, and buckling restrained braced frame. And then for the special case of the special concentrically braced frame, we have to consider what happens after the brace buckles. And that's the most complicated system, because we have both before buckling and after buckling, and we'll do the numerical example of that most complicated system. And hopefully at the end, at least you'll understand this method. Maybe you'll have your own method that you prefer, but at least hope you'll be able to see if your own method adequately addresses the different possible combinations of diaphragm forces and brace forces. All right, so we'll start with wind. And again, note the color coding here. We've got red for analysis. So we have forces applied in our building that are finding their way to our braced frame here, and we can design this connection. We have a consistent set of forces, just one set of forces for each load case, and we design the connection for it. Then when we get to seismic, we have this F sub P force to concern ourselves with, and somehow we need to reconcile that with forces in the braces. Then we get to R greater than 3. This would be the ordinary concentrically braced frame, and the only difference here is that the connections get designed for the omega sub O factor. And so with that omega sub O factor, we need to somehow make an adjustment and design those connections. Then for our higher R systems, the AISC seismic provisions tell us that these connections, these brace connections, have to be designed for the capacity of the system, whether it be the capacity of the brace or the capacity of a link in an eccentrically braced frame. So again, we need to reconcile here 3 sets of forces: the capacity design forces, the F sub P forces, and perhaps the analysis forces. And then we have, for the special concentrically braced frame, the additional concern of what happens after the brace and compression buckles and degrades. And that actually does affect the design of these connections. A little bit of nomenclature. We're dealing with multiple levels, so we're going to call the level in question level I, the brace above level I plus 1, and the brace below level I. Also, we have the bracing connections, which are governed by, for the higher R systems, governed by the requirements of the AISC seismic provisions. But the bracing connections are not just the gusset plates, they are also these connections here through which the forces in the braces are resolved into the beam and column. So those also have to be looked at for the higher R systems using the capacity design methodology. Then we also have collector connections, and all of these qualify as collector connections. And so the collector forces, the F sub P forces, have to be considered in the design of these connections. So starting with wind, as I said before, each vertical force distribution is sufficient. We don't necessarily just have one, but often we do analyze just one. The member forces will be statically balanced. The direction of load is, of course, reversible, and we account for that in our design. Braces change from tension to compression. Sometimes the gravity shear will be additive to the shear from the braces in the beam, and sometimes the gravity shear will counteract the shear coming from the braces into the beam. In order to design these joints, we have to analyze the gusset plate. Often the uniform force method is used or some variant on it, and that's a pretty straightforward method. So here's a free body diagram of the assembly. Again, we're ignoring moments that might work their way through here, and just dealing with the axial forces in these members. We also have shear in the beam, as I said, that could be adding to or counteracting the shear coming from the braces. We have shear in this collector as well, but I'm not going to overly complicate these diagrams by showing all of those forces. Now the force in the beam could be in either direction, or just for consistency here, we'll align it with the force in the collector. The force in the beam might be 0 as well. And you can solve for the force in the beam just using the sum of the forces in the horizontal direction. We've got the collector, in this case, pushing to the right. We've got the brace above in tension, pulling to the right. The brace below in compression, pushing to the left. And then whatever the difference is has to be the force in the beam. You can also solve for the force in the column if you know the force in the column below. So we'll be using the sum of forces in the horizontal and the vertical direction in order to determine forces at these joints. The Gusset analysis, as I said, typically would use the uniform force method, although other methods are possible. It doesn't really matter for today's purpose what Gusset analysis method is used. It's essentially statics. And here's a diagram of the brace in tension. Here are the forces that, or the equations that you would use to get the forces if you were using the uniform force method. Here's a diagram for the brace below in compression, and you'd use essentially the same equations to derive the vertical and horizontal forces at the gusset interfaces with the beam and column. Okay, so for wind, from our analysis, we have member forces. From our member forces, we can get these gusset plate forces. And then for the design of this portion of the connection, we just use some statics. And here, this bright blue arrows that are in this bright blue represent forces that are just derived from statics. And here, for this portion of the beam, or this beam stub, we can also use statics to derive this vertical force in the joint. So here's the sum of the forces in the horizontal direction using just this free body diagram. So we have the collector force, we have the horizontal force from the level above, the horizontal force from the level below, we have the beam force, and we can solve for H connection. Now, we can solve for the vertical force using this free body diagram. We know the shear in the beam. We know the shear coming from this gusset plate, the shear coming from this gusset plate, and the shear on that connection can be solved for. So that's the sort of simple analysis that we will do to derive the vertical and horizontal forces. You do that at the left end. We'll be sticking to the left end in this seminar, but of course at the right end, just given the way that we've applied the forces, the gravity force would be additive to the beam shear. So that's all I'm showing in this slide. That if you look at it on the compression column, that may be the governing case for the shear and the connection right at the face of the column. Okay. So now let's make it just slightly more complicated by talking about the collector force, the diaphragm acceleration F sub P, and the corresponding collector force. As a reminder, we typically have a simplified vertical force distribution that we use for the design of our braces. And then we have a different set of forces that we use to check our diaphragms. And the reason we have this, you can think of it as trying to capture the response of a building that isn't just in that first mode. So we have some forces associated with the first mode. We have some forces associated with the second and third mode. And you can look at them in a simplified way, the way the code does, applying these periods, these modal periods, to a response spectrum. And you can draw an envelope of the forces. You can draw shear and overturning diagrams based on modal combination. And from that sort of simplification of the building response, the ASCE7 vertical distribution was derived. And the vertical distribution does two things. It gives us perhaps appropriate shear to design for in our braced frame or shear wall at every level. And it gives us appropriate overturning to design for it at every level. So that's the basic system. However, the vertical force distribution that we use often has very little force entering the frame at the lower levels. And that's okay for the design of the braces and column of the frame, but it's not okay for the design of the diaphragm and collectors. It's really underestimating the potential forces that can happen at that second and third floor. And so what ASCE 7 does, it tells us, well, at a minimum, we have to look at these F sub P forces that are going to be greater than what we get from our vertical distribution. And so we get a different set of forces. Those will capture the maximum force, or those are intended to capture the maximum force that might enter our frame at every level. But if you applied them all at the same time, you would end up with a grossly overestimated shear demand and a grossly overestimated overturning demand. So we don't apply them all at the same point. Okay, before we bring this to bear exactly on our design of that frame connection, I'll just say that we need to take those F sub P forces and somehow get them to be collector forces and into our braced frames in this example. So just for simplicity, we're going to do a very simple design and assume that the force ends up as a uniformly distributed collector force, so that it's essentially 33% of the force goes to this bay, 33% of the force to this bay, and 33% to this bay. You can design this collector system in any number of ways. You could, if you wanted to, you could assign 100% of that force to the center bay. Of course, there are some implications to that we won't get into in this seminar. But for simplicity, I'm just saying 33%, 33%, 33%. Whatever your assumption is, it affects how you design these connections. And so I'm presenting my assumption up front. It may be different from yours, but the following slides will be consistent with this assumption. Okay, so as we said, the vertical force distribution is insufficient. We will therefore look at both the vertical force distribution and the F sub P force, but we're not going to look at them. We're going to look at them separately in two different load cases, and I'll explain a little bit further. Case 1 is just going to be that vertical force distribution. Same procedure as wind. So we make sure that we're designing our connections for those forces that correspond to what we're designing the braces for. The member forces will be statically balanced, and really we can proceed with our design as normal. This is typically going to govern the vertical forces at the connection. Then we're going to create a case 2 and use a statical adjustment in order to have a consistent set of forces. Case 2 is going to look at our F sub P force, but by bumping up the force, the collector force, to the F sub P level, we're creating an imbalance from statics, and so we're going to do a statical adjustment to get back into equilibrium. And then as a reminder, when we're in seismic design category C, we need to apply the omega sub O factor. This case 2 may govern the horizontal forces at the connection. Often it does, but I think there are some circumstances where it may not. So here's case 1, looks very much like wind. We have our horizontal force distribution. We analyze and we get a consistent set of forces, meaning that if you apply static equilibrium, you should get the sum of the forces equals 0 at this connection based on forces from your analysis. Now the case 2, we're swapping out F sub P at this level for the F sub I at that level. So we're increasing the force coming in at this level. So we're no longer in static equilibrium at this connection. If you do the sum of the forces in the horizontal direction, you're probably getting extra force going to the right. So what we're going to do as an adjustment, is, and here's the distribution that I talked about before, some percentage is coming in from the left and some percentage is coming from the right. We're going to use statics here to reduce the tension in the brace above. We're going to say when this force is bumped up, it means more of the force is coming in at level 3, and as a consequence, less of the force is coming from the levels above. So then we have static equilibrium just by bumping or by reducing that brace force slightly, and we can design that connection then using static equilibrium. So here's the equation for that force in the brace. It simply has to do with subtracting out the horizontal component of the brace below, subtracting out what's coming in from the collector and the beam at this level, considering the F sub p force, and then doing the trigonometric adjustment. Now, if you were very conservative, you could say, well, instead of reducing the force above, why not increase the force below? And I would say the code doesn't ask you to do that. The code doesn't ask you to design that brace for more force than the base shear will tell you. And so that is not something that the code requires, and in fact is inconsistent with the code requirements. So even though I acknowledge that that would be one method of doing it, I think it's inconsistent with the code and would suggest it's overly conservative. Okay, so up to now I've been talking about seismic forces using that equivalent lateral force procedure vertical distribution. A lot of people use modal response spectrum analysis, which requires me to introduce a new color, purple. Basically, the procedure is fairly similar, but the modal response spectrum analysis introduces a couple of complications. One is that the members lose signs, so the forces are all given as positive because we're taking the square root of the sum of the squares or some other modal combination. And also, because they lose signs, we have to decide on the direction of forces for the design of these things. Similarly to the other conditions that we had, the member forces are not statically balanced. We're taking the modal maximum or the modal combination maximum of each brace force and perhaps the collector force as well. And these maxima may not occur under the same conditions, and so we don't have a statically balanced set of forces. So for the case 1, where I said it's pretty simple, you just apply your lateral forces and design your connection, there might be a slight adjustment required. So in this case, I'm suggesting we adjust the collector forces to reach static equilibrium. And then for case 2, we adjust the brace forces as before. So here's my representation of forces that come out of modal response spectrum analysis. We don't know which direction they go. Well, as engineers, we pick a direction. So if we're designing this as if the column is in tension, we're going to assume that the brace below is in compression and that the brace above is in tension. Now, mathematically, there's no reason that we need to do that for the modal response spectrum analysis, but this is how we understand the buildings to work in an earthquake. So that's what we're going to do. Now, as I said, there's an adjustment that needs to be made. And that adjustment, I'm suggesting we can reduce the force entering the frame at that level, assuming that more of the force is coming from the level above through the brace above, and reduce what's coming in there. So case 1 puts more of the emphasis on the braces, and we get design forces that might govern for vertical. And then case 2, we'll get to case 2 in just a moment. Case 2 adjusts the force in the braces, putting more of the emphasis on the collectors. For collectors, we model the collectors. We can model the collectors and get the modal combination forces for those collectors. That would mean having flexible diaphragms, or not having rigid diaphragms, I should say, at each level. Or we can use section cuts in a lot of our software programs to determine how much force is entering the frame or wall for each mode. As a reminder, anything that we're interested in, any quantity of interest in a modal response spectrum analysis really has to be tracked mode by mode. You can't use the difference between maximum combinations in a modal response spectrum analysis. That is mathematically meaningless, and for design purposes meaningless as well. Here's our case 2b. We're putting in our F sub p force as ASCE 7 requires, and then we need to do a statical adjustment in order for the sum of the forces in the horizontal direction to equal 0. Omega sub O, which comes in for in seismic design category C, what we do is typically as we do our analysis, we combine our forces, and then we apply omega at where required at the end. So it's required for collectors in seismic design category C, and we apply it for everything that's part of the collector connection. And then omega sub O is part of a load combination that includes gravity loads. So we'll do a quick example here. Here's our 4-story braced frame. From ASCE 7 with an R of 3, we get these forces entering into this frame at these levels. ASCE 7 also gives us these F sub p forces to design for. So we're going to reconcile the two using this two-case approach. Here are the forces consistent with the lateral analysis. We have 226 kips above, 269 kips below, and then here we have 60 kips, 20 coming in here, 20 coming in here, and 20 coming in here, and of these 20, half go left and half go right. Okay, so we do a gusset analysis for the brace in tension, we do a gusset analysis for the brace in compression, and we get the forces that we'll use to derive the rest of the forces in the connection. So here's a free body diagram of the column. I'm not really concerned with the tension in the column, that just goes straight through. But I do have the forces applied by the brace, so the brace pulling up here and to the right, and the brace pushing up and to the left here. I've got the collector force in there. And I can use statics for the sum of the forces in the horizontal direction and get, there's just 9 kips there in that connection. Then I can do a free body diagram of this beam stub. Again, we've got the brace pulling up and the brace pushing up. I'm not showing any gravity here, but that would be additive, of course. And I solve for the seismic force here, and that's 123 kips. And also, here's that 10 kips that we derived earlier. So that's case 1. Now let's look at case 2. Case 2, we're keeping that force from our analysis in the brace below, but we're looking at diaphragm forces here corresponding to F sub p, which instead of 60 kips was 120 kips, so essentially doubling those forces. F sub p is twice F sub I. And then we do some statics here to figure out what the corresponding horizontal component would be in this brace, and therefore what the tension is in that brace. Pretty straightforward. Then we simply redo the gusset analysis based on this lower force level. We have the same gusset analysis for the brace below because we're keeping that same compression force. And then we do statics at the column and solve for a larger horizontal force here. That makes sense. We have a larger collector force, larger horizontal force. We do statics looking at the sum of the vertical forces for this beam stub, and we get slightly lower vertical forces, which makes sense because we have less force in the tension brace above. And then we summarize these. So here are the forces that we're looking at that we use statics to solve. Case 1 gives us the higher vertical forces at the face of the column and in the beam stub. And case 2 gives us the larger horizontal forces, both the collector force outside of the connection and the horizontal force going through that connection. So there you go. And then if omega applies, we simply apply omega. In this case, omega is 3, and so it gives us quite an increase in force here, and we could also apply omega in case 1 as well. If you wanted to, you could design the connections here for the vertical and horizontal for case 2, and then also for case 1, check it separately for each of these. Or if you want to be a little conservative, you could take the maximum vertical and combine it with the maximum horizontal. In some cases that will be slightly conservative, in some cases that might be extremely conservative. If we're representing these forces to a connection designer, it would be useful to give it as 2 different cases. If you give it as the maximum of each, then the connection designer will have a statically inconsistent set of forces and might have to do another adjustment and add another bit of conservatism on top. So in summary, case 1 governed for all of these forces, and case 2 governed for these 3 forces. All right, we're, I think, about halfway through. Brent, were there any questions that you wanted to address at this point?
Yeah, Raphael, we do have a couple of questions. Let's just take a moment to address these, if you would. The first question is in regards to the omega factor. Does omega apply to the column in the brace/collector connections?
So the question is, does omega apply to the column? For the R equals 3 system, the column is not required to be designed for omega. However, anything in seismic design category C, what is part of the collector connection does get designed for omega. So as I showed you, the design of the collector to the column and the column to the braced frame beam is also part of that collector system. Those do get designed for the omega level loads.
Okay. And then the next question, if you're using a design software, how and from where in the model do you extract your collector forces?
That's a good question. So if you're using a design software package, and I won't name any names, the ones that I'm familiar with these days, which is something I would have loved to have had when I was doing these analyses starting out in my career. Most of them have what we call section cuts, which means you can assign a sort of virtual member that represents the difference between the shear in your frame above and the shear in your frame below. And if you're doing an equivalent lateral force analysis, you can use that section cut simply to capture the force that enters your frame at that level. You have to then step to the diaphragm analysis or to use some engineering judgment to decide whether that all comes from the beam outside of the frame or how much of it comes from the frame beam itself, and do that distribution. But you can use the section cut that tells you how much force is entering the frame at that level. And the same goes for the modal response spectrum analysis. As long as you have the section cut following the same modal combination rules, which it will, you get the maximum combination of forces entering the frame from each mode.
Okay, thank you.
All right, so let's proceed on. R equals 3.25, that's the ordinary concentrically braced frame. Very similar to what we were doing before. The only difference is that you have omega sub O applied to the bracing connections as well. So we'll have the same 2 cases, the vertical force distribution, and then combined with collector forces that are determined by statics. And then case 2 we will substitute out the F sub P force for the force from the analysis, and we'll need to do the static adjustment on the brace above. And again, we're applying omega sub O to all elements of the connection. So here's case one. We're simply taking our analysis forces. They're all statically consistent, so we don't need any adjustments. They're all statically consistent already, and we apply omega sub O to each of these and get our connection forces. Here's case two. Now, with the introduction of the F sub P force, we're no longer statically consistent, so we have to make an adjustment here. And the adjustment here is to reduce some of the force in the brace above. Okay, now let's look at what's a little bit more complicated, the R greater than 3.25, the special systems. The vertical forces, we're not really designing this frame for the base shear forces anymore. We're designing the connections, or I should say the frame is designed for the base shear forces, but the connections are designed based on the anticipated yield mechanism. Here's the anticipated yield mechanism for the special concentrically braced frame, eccentrically braced frame, and buckling restrained braced frame. So case one, we're going to look at forces corresponding to that yield mechanism. We will apply the forces, those yield level forces, and use statics to solve for the horizontal force. Case two, we have the F sub P force to deal with, and we'll use statics to make a consistent story there. So we're doing a sort of system level analysis based on the mechanism. Omega sub O doesn't really apply. These are all forces that correspond to the capacity of the system, so we don't need to apply omega sub O. All right, so here's the mechanism for the special concentrically braced frame. We have the yield capacity of the brace above. We have the full expected compression strength of the brace below. For the eccentrically braced frame, it all comes from the yield strength of the link, which is multiplied by 1.25 to represent strain hardening. And from that, we use just a little bit of statics to determine the corresponding force in that brace, and we use the force in that brace then for the design of the bracing connection. All right, and so if we're designing this bracing connection, then we need to know the force in this brace, which comes from the link strength above, and we also need to know the axial force here in this beam, which actually comes from the strength of this link beam below. So we need to actually analyze both of these levels in order to get the design forces for the connection there. And buckling restrained braced frame is kind of similar to the special concentrically braced frame. We're taking the maximum forces that correspond to the yield of the beam of the brace above. This would be in tension. So we have the area of the core, we have the yield strength, we have an RY factor for material overstrength, and we have a little strain hardening factor here, and for connections we throw 1.1. For the brace below, it's the same thing, but there's a compression overstrength factor as well. And so then we design the connections. For each of these, we have brace forces that really correspond to the yielding either of the brace or the link beam above. Here we'll just pretend it's of the brace, or we'll assume it's of the brace. So we have the maximum forces above and the maximum forces below. For case one, then, we simply use statics to tell us how much is coming in at that level. So we take the horizontal component of these brace forces and the horizontal component of the brace forces below, and then the difference is the force coming in at that level. Whether it comes in all in the center or is spread into 3 equal parts or whatever other distribution is possible, that's part of the overall diaphragm approach, Here in this example, I'm always using 33%, 33%, 33%. Okay, so that's case one. So here we go. We've used statics to solve for these forces, and it's consistent with the story mechanism, so we don't need to apply omega sub O. Case two, we're bringing in the F sub P force. And here ASE is a little bit funny in how it treats omega sub O, and I know I'm a member of that committee, and the committee's gone back and forth a couple of times. But just to be consistent with a more conservative interpretation, we're applying omega sub O to F sub P, which I know there are some issues with. We apply omega sub O to F sub P here. We use our capacity design forces for the braces below, and for the braces above, we reduce them by some factor so that we end up with the sum of the forces in the horizontal direction equaling 0. So we know the capacity of the level below, and now we do a static adjustment to get the forces in the level above, in this case 2. And then we have the distribution of that collector force. So here is, case 2. These really should be yellow arrows. I'm sorry about that. I was very careful about my color coding, but I got it wrong on this one. So these should be yellow arrows here because they're from the diaphragm force. If we have this is a unique situation, but I'll go through it anyway. Here, if we bring the brace forces to a link beam, this link beam really acts as the fuse for 2 levels at the same time. So we could really design this link beam as if 100% of the force causing it to yield came here, or 100% of the force causing it to yield came here, or we could make some reasonable assumptions about the distribution above and below. If we take the absurdly conservative one, which is 100% could come here or 100% could come here, that's really going to affect the design of these connections and make them very, very conservative. So what I suggest is that we simply look at possible distributions that correspond to what ASE 7 asks us to look at. So how much comes in at level I and how much comes in at level I plus 1? I say let's look at 2 different cases. Case 1 follows the vertical distribution, which might be triangular. If this is a 2-story building, that might mean that 67% comes in here and 33% comes in here, so we end up designing this connection for 67%. And then case 2 corresponds with our F sub P forces. And with our F sub P, we might end up then designing, assuming that equal forces come in at these 2 levels. So if this is 67, then this might end up being 50%. And so we've got a little bit of an envelope going there. Okay, so that's the approach that I would suggest, but there are other approaches possible. Okay, and so it's just based on the ratio of what you get either using the vertical force distribution for the equivalent lateral force procedure, that would be case 1, or swapping out that F sub P for case 2. So that's the mechanism design approach. Now, the special concentrically braced frame has one more mechanism to consider. We not only consider the maximum forces in the braces, we consider what happens after the brace buckles. So we still have case 1 and case 2. They still apply. Case 1 being the maximum forces in the braces, case 2 being that maximum collector force. But now we introduce a case 3 that captures our post-buckled condition. So returning to the code requirements, the code tells us for the special concentrically braced frame, we also have to consider what happens when we lose about 70% of our strength in compression. And what we'll see is that the force distribution changes quite a bit, and it does affect the design of these connections. So here's that same frame that we've been looking at. We have, let me erase that. We have for the braces above, we have the maximum force, and we have this post-buckled force for the brace and compression. Similarly, for the braces below, we have the maximum tension force and then this post-buckled compression force. These are given to us by the AISC seismic provisions. Then for static consistency, we determine the collector force, or the force entering into the frame at this level. So case 3 is very much like case 1, but with just different compression forces. So we start by determining the shear capacity of the level below and above, and the difference is what's coming in at this level, and of course the distribution is up to us as the engineer, whether it's 100% in the middle bay or 33%, 33%, 33%. Doesn't really matter. Well, it does matter in the design of the connections, but we are free to determine an appropriate load path for the diaphragm shear. Okay, so here let's do the statics. We've got the brace above pulling quite hard to the right, and we've got the brace below pushing just a little bit to the left. And what that means is the force in this beam is going to end up being very high. It's going to have to push very hard to the left in order to counteract what's coming in and what this tension brace is doing. So that's for the configuration with the brace below. When we have this stacked chevron configuration, we do the same thing, and we also determine that there has to be a high compression force here in this region of the beam. So in this case, we do the same sort of statics. Maybe the statics gets a little bit easier because there's no brace below, but you can see this force in the beam now has to be even greater to counteract what's going on there. Plus, as we all know, there's shear in the beam from that unbalanced force that has to be accommodated in this connection. If we have this sort of configuration, it really should be thought of as a single braced frame with a very long connector as part of it. And so in order for this system to work in the post-buckled condition, a lot of the force has to flow, has to zigzag, and will affect the design of these connections. And that's something that the code hasn't exactly said explicitly, but is consistent with how we design this system. So again, we determine the capacity above, capacity below, and then we analyze the connections and make sure that we have a load path connecting them. If we have an asymmetrical condition, well, that makes it a little more complicated. If it's asymmetrical, we have to consider one set of forces here with two braces above in compression and one brace below in compression, analyze what's going on in these beams, and then we have to turn around and do the asymmetric case, the corresponding asymmetric case here with only one brace above in compression. And the forces and the connections will be quite different in these asymmetrical cases. All right, so now we're ready for the final example that puts it all together. For the special concentrically braced frame, here are the lateral forces that ASCE 7 gives us, the vertical force distribution. It's pretty much triangular. Here are the braces that we end up designing at these two levels. So this is the brace at level 3. This is the brace at level 2. And here are the F sub P forces that ASCE 7 gives us. Okay, So we'll start with case 1. Case 1 is the capacity design with the maximum compression and tension forces. So here's the maximum tension force for this size brace. Here's the maximum compression force for this size brace with this brace length. So the corresponding shear for this frame at this level is just the horizontal components of each of these forces. We do the same thing for the level below. We take the tension and compression, do a little trigonometry, and we get that shear. And the difference is about 90 kips, which I'm going to say is 30 kips, 30 kips, 30 kips. So now we go into the gusset analysis based on those maximum brace forces. We get the vertical and horizontal forces on the column, vertical and horizontal forces on the beam. Do the same thing for the brace below. This brace is in compression, has somewhat lower strength in the compression direction. Then we do our free body diagrams and apply statics. So here the sum of the forces in the horizontal direction tells us that we have 48 kips at that joint. And then here we do the sum of the forces in the vertical direction, and it tells us that we have 211 kips here. So now we have forces that we can use to design these connections, but that's only one of the 3 cases we need to consider. So case 2. For case 2, we keep everything below the same. We still have to design for this mechanism, so all of that stays the same. But we apply the omega sub O collector force. So that already has omega sub O in it. I should have indicated that. That's twice the F sub P force. And using statics, I can solve for the difference, and that's the horizontal component of the 2 braces above. And so using trigonometry, I get that 280 kips there. So I do my gusset analysis based on 280 kips. I keep the gusset analysis I had below, and then I can take those forces, apply them to the column. I can take those horizontal forces, apply them to the column, and use the sum of horizontal forces to solve for the force here at the beam stub to column connection. That's 60 kips about there. And then I do the sum of the forces in the vertical direction here and solve for the vertical force, which is 166 kips. Also, I solve for the horizontal force in the beam, although this isn't going to be what governs. So now case 2 is covered. This covers us for omega, and I'm sorry, for the collector force times omega. And now I need to look at case 3. Again, case 3 is very similar to case 1. What we're doing is taking the member capacity forces for the diagonal braces and using statics to tell us what's consistent with that in the beams. Again, based on the capacity of this brace, I have the same 462 kips I had in case 1. But now I'm taking 30% of what I had in case 1 for the compression, and that ends up being about 100 kips. So if I put the horizontal components of these together, and I think these are all at 45 degrees. I think that's how I did all this analysis. And that gives us about 400 kips in the level above. We do the same thing at the level below. Again, it's based on the brace size that we've used. If we used a larger brace size, we would have larger forces. We have the same tension that we had in case 1, and then our post-buckled compression for case 3 is 30%, roughly 30% of what we had in case 1. So we do the trigonometry here, and we get 460 kips, and the difference is what, about 60 kips. So very, very little force entering into this frame at this level. Here's the gusset analysis, the same one we used in case 1. Now here's the gusset analysis of the brace in compression. using 116 kips as opposed to what we had, which was about 400 kips. And we get these lower forces applied at the face of the column and at the beam stub. We draw our free body diagram at the face of the column. Free body diagram of the column segment. Again, we don't really care what the tension is in the column. That flows straight through. We're just using this free body diagram to tell us the horizontal force at this joint, which is 107 kips. And then we solve for the horizontal force here, which is 266 kips. And this is really what's going to govern for the design of the beam. That was 10 kips in our elastic analysis, and it was a lot smaller in the other mechanism analyses that we did as well. So very important to apply these principles both for the design of the joints and also for the design of the members. So this joint gets designed for quite a bit of force, 266 kips. And then we do the sum of the forces in the vertical direction, and we get 144 kips. So let's summarize then for the design of the different joints. Here's the beam stub to column joint. Here's the beam stub to beam joint. Case 1 gives us the maximum vertical force there. Case 2 gives us only the maximum collector force outside of the connection assembly. And case 3 gives us the maximum horizontal force, both within these joints and also going into the beam. So you could either design these joints for both case 1 and case 2, or you could, if you wanted to, take the maximum vertical force and combine it with the maximum horizontal force. That looks like it'd be a bit conservative here, and it certainly wouldn't be required. But it's good to understand what the governing forces are. If we're communicating these forces to someone else to design these connections, we have 3 cases, and we really want to be communicating 3 sets of corresponding seismic forces in each of these, or I guess, corresponding forces in each of these members to be applied at the connection. So to summarize, to summarize graphically, here's that connection again. Case 1 is giving us maximum values for each of these forces, so not a surprise. When we design the gusset plate for the maximum tension force, that's going to govern, as we'd expect, for its connection to the beam and column. Case 2, which is the F sub P force coming in with the omega value, that really only tells us the maximum force outside of the braced frame. The mechanism forces are going to govern within the braced frame. And here's case 3, and that tells us the maximum horizontal force in this joint and the maximum horizontal force in this joint. So really we couldn't design this connection adequately without looking at 3 different cases. Now we might lump our maximum forces together and just design it once, but in order to get the appropriate design forces for this connection, it really does look like we need to examine 3 different cases, each of which is based on the mechanism of the special concentrically braced frame, but has different assumptions about how the lateral force is coming in. All right, so that's the final example. Now, a couple of words in conclusion. We had 3 types of forces to be reconciled for the design. We have the base shear forces, which apply for wind design for R equals 3, and they also apply at R greater than 3 although they may be superseded. So we could use the equivalent lateral force procedure or the modal response spectrum procedure. When we get to seismic design, we have the diaphragm accelerations that are inconsistent with the base shear forces. So these already apply for seismic design category B and C. At seismic design category C, we have the omega sub O factor that's introduced, but that's fairly easy. And then for our more ductile systems, we have mechanism type forces, and each of those mechanisms has its own requirements in terms of determining the brace forces, but we have to follow those brace forces through and combine them with the diaphragm accelerations that the code requires us to look at. So the diaphragm accelerations really are ASCE 7, call it A7, and the system forces are really from AISC 341. So combining those two requires a little bit of manipulation in order to tell what I'll call a plausible story about where the forces are that we can use as engineers for design. Understanding the purpose of the design loads is, I think, key to applying them in a meaningful way. The forces can be reconciled by artificially creating two different load cases to derive design forces. One of those based on the vertical distribution or the mechanism forces, and the other one putting in the F sub P force and then making an adjustment. There's a third one for the special concentrically braced frame. So case 1 has the base shear forces or mechanism forces depending on what type of system it is. And then case 2 includes the diaphragm accelerations and with some of the mechanism forces and some adjustments made to satisfy statics. Load cases can be consolidated for simplicity. Typically, case 1 is going to result in the maximum vertical forces at the connections, and typically case 2 will result in the maximum horizontal forces, unless of course there's a case 3, in which case 3 typically gives you the maximum horizontal forces. When we apply omega, which we're required to starting in seismic design category C, typically we apply omega to all of the analysis force E. We never apply omega to the mechanism forces. For R greater than 3, we have the mechanism analysis, which supersedes omega sub O. Omega sub O still applies for collector and diaphragm forces. Okay, so hopefully that makes sense of a lot of the different requirements that we have in ASCE 7 and the AISC seismic provisions. Gives you some tools for combining the two into a reasonable set of design forces that you can use on your projects. So we've got time for questions. I know we had just a couple in the middle, but we do have time for full question period right now.
Okay, thank you, Raphael. We do have a few questions right now, but I'll just echo what Raphael said. If you have any other questions, please feel free to send them in via the chat right now. For the first question, can you go to slide 77, please? So the question that came in is in regards to using 30% of the load for compression. Can you please repeat the explanation as to why we're using 30% when determining the minimum?
Okay, so I'm going to go up a few slides to the, here we go. This is the AISC 341 requirement for special concentrically braced frames. In addition to, so there there's a special analysis required for many of these ductile systems, and that analysis has to do with the effect on the frame of the maximum forces from the braces. So if you turn to F2.3, which is where the analysis requirements are for this system, there are two different set of analysis requirements for special concentrically braced frames. The first one, I'll make it fairly simple. The first one tells us to look at the maximum tension and the maximum compression and figure out what's going on in the columns. This will give us the maximum overturning, what's going on in the beams. Then there's a second analysis, and that tells us to look at the maximum tension force again, but look at compression being degraded to 30% of the maximum compression capacity. And the reason is, you see this brace as we go into large lateral deflections, the braces in compression are buckling. And as we go out to larger and larger drift, they buckle and they bend. It's kind of like a flexural plastic hinge might form in the middle of these braces in compression when they get out to large enough drift. And they never quite work the same in compression again. So as the earthquake goes on and they buckle 2, 3, 5 times, they get softer and softer in compression, and they get less and less effective. And so arbitrarily what we did on the code committee is select a level of degradation down to 30% of the compression capacity and say analyze your system at that level of brace degradation. Make sure that this beam, let's say if we have a chevron condition, we have a big tension force from the brace working in tension and a small compression force here, make sure that this beam doesn't bend too much, that it doesn't yield in bending. If we design based on those criteria, we feel that we get a system that performs adequately. When it comes to the design of the braced frame, we have that post-buckled compression here and post-buckled compression there shown in green, and the full tension there. In order for this system to work, after this brace here is degraded and this brace here is degraded, in order for the system to work, we really have to drag a lot of force through this beam over to here. And the provisions have this analysis requirement so that we will have designed this beam for some axial force, not necessarily the axial force that it absolutely will see in an earthquake, but if we designed it based on this mechanism, we feel very comfortable that it's not going to buckle or we're not going to fracture these connections based on how the load distribution changes as these compression braces degrade. Kind of a long-winded answer, but it's a very important point, and it does, as you saw in the numerical example, it does have a dramatic effect on the design of that connection and the design of that beam.
Okay, and then a follow-up question for the SCBF. Is it also necessary to analyze case 2 with the post-buckled mechanism forces?
That's a good question. Case 2, in the example that I showed with the collector force, it really only gave us the maximum force outside of the frame. It didn't give us the maximum force inside of the frame. So I would say generally, if you analyze case 1 and case 3, you probably have what's going on inside of the frame covered, and you don't need to worry about case 2. Outside of the frame, though, you do need to worry about case 2. Okay, next question. You talked about using a diaphragm force distribution of 33%
for three bays. Is this purely an engineering judgment? Do we get to decide how long of a collector we want to use? For example, can we use a partial building width versus a full building width, et cetera?
Yeah, that's a good question, and an important point. It has implications for design. So here let's just confine ourselves to looking at the three bays. The three bays that we have here, assume that's the whole building length. Some engineers really don't like to use the full building length, and will say, how many studs can I get into this beam? Can I get 100% of my lateral force from the diaphragm into the beam directly? Or maybe they might use just a limited length and discount the rest as the collector. And I really don't see anything in ASCE 7 or elsewhere that tells you you can't do that, but you do need to make sure that you have a load path to engage, to concentrate your shear in the length of the collector that you're considering. And also, it does have a little bit of an effect on local chord forces. We're not getting into the design of the diaphragm here, but the way that you get axial forces in your chords is to have shear adjacent to those chords. And so you, instead of having a beam that is the full rectangle of your floor plate, if you're only using the shear here and the shear here, maybe your beam kind of looks more like a little bit like, I don't know what that is, a sort of truncated football. And that may affect the magnitude of your, either it could affect the magnitude of your chord forces, or it could just be a question of what your load path is. If we're dealing with a reinforced concrete fill over metal deck, you probably don't have to worry about the load path too much within that. If you check the section here adjacent to the braced frame, it's probably okay at the other sections. But if you have just a metal deck, that load path becomes, or just the steel deck, that load path becomes a little bit more complicated, and you need to do a little bit more work to deliver that force.
Okay, can you go to slide 82, please? Okay, this is the question, and I'll do my best to bring the question out. It's and what was commented on. In slide 82, you show a force distribution for this frame line, accounting for what appears to be two frames as one frame. What exactly is the difference in the case of the SCBF that causes several frames along the same line to be accounted for as one frame?
Okay, that's an excellent question. Okay, what do we have any? So the what's different about an SCBF is really that the system depends very heavily on the tension braces. So if we imagine that we have a lateral force here pushing us to the right, such that the compression braces become ineffective, they buckle, they lose 70% of their capacity, and that 70% is really arbitrary. In tests, if you rack the frame long enough, the braces essentially fracture and maybe even disappear from, they become totally ineffective. But for our purposes, let's assume that these braces lose a lot of their effectiveness in compression, but are still participating a little bit. So I'm trying to make them, a little bit hidden here by graying them out. Okay. So for this system to work, then it really needs to be able to take the force here from the roof, drag it here, and it's not going to be able to go through this brace, so it really has to find its way over here. And then over here, it's not really going to be able to, most of it won't be able to be handled by that brace, so it really has to be dragged back. So it's this sort of zigzag path that has to happen. Now here, I'm drawing it in the same line. You could have another braced frame that is 30 feet away or 40 feet away out of the plane of the page, and some of that load could be sent, instead of in line of the braced frame, it could be sent via shear in the diaphragm to that other braced frame. But really the idea is, for the special concentrically braced frame, it's good to imagine how the system works if all the braces in compression disappear. And that gives you, that's not what the code asks you to design for. The code allows you to use a degraded 30% capacity. But for simplicity's sake, if you just take those braces out in your mind, you get an idea of this post-buckled or this post-elastic load path that has to be provided. So when the compression braces degrade, we need to be able to have a significant transfer significant axial forces along this zigzag load path in order for the system to work.
Okay. Question regarding collectors. For beams in compression, I apologize, let me start that over. For beams in compression, do you ever consider composite action with the deck? And what are some of the considerations there?
Yeah, I think the code definitely allows you to consider composite action, but it does introduce some additional considerations. One is how the load gets into the concrete. So if looking at this frame that's on the screen right now, we have load that's in the brace, in the gusset, flows through this connection into this beam, and then at the other end of the beam flows into this gusset. You could have a composite deck here, but it's pretty hard to throw a lot of the load immediately from the beam into the deck and then get it out of the deck back into the beam. So it's a question of how much you can engage that composite deck. If you have several bays of collector, let's say we look at this load path, maybe you can throw a lot of the load into the deck here and get it out of the deck over here, and maybe that takes some of the heat off of these two connections. So depending on what your situation is, it might be easy or not so easy to engage that composite deck as part of your system, part of your collector.
Okay. Next question. When designing connections for mechanism forces, do the phi factors apply to the capacity checks?
Yes. So when designing members for mechanism forces, the AISC method gives you forces that you're expected to use along with the design strengths that you have from the main specification. it's a little conservative, and it's possible that in the future there may be adjustments made to eat into a little bit of the safety factor that we have there. But at the moment, that's what's envisioned, that you use the design strengths that come straight out of the main manual.
Okay. And last question. In using commercial programs where the diaphragms are defined, what are the recommended brace forces? Should we still modify the brace forces according to today's lecture?
So if you're using rigid diaphragms with defined brace forces, I don't think that really changes anything. I think if you're looking at case 1, you should have a statically consistent set of forces from your analysis. The rigid diaphragm won't tell you the collector force, but you can sort of figure it out. Either if you're doing equivalent lateral force procedure, you can figure it out from statics. If you're doing modal response spectrum analysis, you definitely have to use those section cuts. And then for case 2, you're doing a statical adjustment anyway. You're getting your F sub P force. Outside of your analysis, and then using the brace forces below. So I don't think the rigid diaphragm interferes with this at all.
Okay, well, I think that wraps up our Q&A. Thank you all for your participation in that, and thank you, Raphael, for your answers and an excellent presentation today.